So in this part of the course, in this specific clip, we're going to look at density matrix for compound systems. And we have seen this is important if we want to eliminate some correlations that occur when you have entanglement. So let's have a look. How are we constructing this? And what do we care? Well, we have already done density matrices for isolated systems, and now we need to generalize this. So what I can already tell you is that they are constructed in the same way as for isolated systems. Using the basis AJ tensor product BK. And just to remind you, this is the tensor product of the orthonormal basis AJ and BK. This means if we say we construct this in the same way, we can write this as whole sum of JK LM whole JK LM. I'm going to write it like this because it's easier. AJ BK AL BM. So this is writing the density operating matrix formulation, but considering now that we have a compound system. And here we have whole JLKM is AJ BK sandwiched with whole and the cat is then ALBM. So far, so good. Theoretically, I mean, we expected that because we have been compounding things, if you want. And we would like, because we mentioned about reduced states and we have brought this mysterious concept in the previous lecture, we would really like to know what this is. So we're going to have a look at reduced states. And what do I mean by reduced? For entangled systems. This is something sometimes that you need to use. And what do we call this? So the reduced state, so it's going to be let's say we consider again systems A and B, and the reduced state for system, so assumption, systems A and B, which are entangled. The reduced state for system A or B is the state which allows someone to calculate the value of any observable which acts solely on system A so or if you wish for any measurements of the properties of A which ignores B. So what we wish is we want to ignore B, but the difficulty is that A and B are entangled. So you need to have a reduced state. You need to find a way to remove that information. You need to measure the properties of A, ignoring B, or the other way around, but they are entangled from the start. So what are you going to do? And this is obtained by calculating the partial trace, which is what we're going to see right now. What is the partial trace and what it means? And we're also going to discuss some examples. So let's consider we have a compound system, and if we get this expression for ρ, which we have before, right? We're going to have a look at the trace of ρ. So we start from a compound system, and we can say that the trace of ρ is going to be sum over jk, ρ jk, jk. Remember that ρ jklm is aj bk, ρ al bm. So pretty much what you do is like what you do in trace, you are considering the diagonal elements of this matrix, whatever you have, right? So you consider ajbk and here also ajbk, and you have the whole here, and then you compute the trace of whole. Agree? Now, the concept of a partial trace is to delete a system from a tensor product compound system. And you're going to get then the reduced state. So the partial trace, and we're going to see right now what this is, deletes a system from a tensor product compound system. Meaning, if you have, for instance, a compound system A, which is in this space AB, if you want to delete B, you need to apply a partial trace. And what you're going to do is this partial trace gives us a reduced state of the remaining system, which is what we had when we had these two spins that I said, okay, what does the physicist A see? What does physicist B see? You could see that if you would remove the information, you wouldn't see that the other particle had the spin up or down. You would still get a coherent superposition. So there was no contradiction. But the mistake was that people were thinking about a separation from the start, and you didn't have, because the system was entangled, so you needed to treat the system as a whole. And we're going to see now how we calculate these things. So this is a definition. How do we trace out? What we have is, we have to sum up over the indices when you have the traces and when you have the matrices related to the density operator. You have to sum up sum over the indices for system A alone. For instance, if you have trace of A for Rho, you have ALM, and then you have this trace which you had before, JLJM, BLBM, and this is equal to Rho B. So this is the reduced density matrix, and it would describe the state of the system B if this is considered individually. For instance, some of you so probably if you are working on a research problem, you have already heard that sometimes you integrate over degrees of freedom, or you integrate over things you don't need to see to focus on the system which is going to give you the information. So effectively what you're doing is you are tracing things out, and you are using this concept of reduced state. So we're going to see here some examples, and if you want to define for the other subsystem, you just have to do the sum over the other degrees of freedom. So similarly, the reduced state for system A is obtained by tracing out the coordinates and the indices related to B. This can be used for everything, degrees of freedom, particles, etc., depending pretty much on the problem that you're looking at. So you have rho, J, L, K, L, and you are summing over L, and then here you have A, J, A, K, and this we call rho A. So you have then the reduced state of the system A, and here you have the reduced state of the system B. And for expectation values, what we need to do is we need to compute the way we have seen already for density matrices. But if we want to consider an observable that acts solely, let's say, on state B of observables acting only on B, on the system B, which means that you are doing a measurement on B alone. Let me emphasize this. Then you will have that the expectation value in this case is going to be trace of the operator applied to rho, but B. You take the reduced density matrix. And an important observation here, especially if you're talking about entanglement, is that the reduced state of an entangled state is always a mixed state. Which means that your density operator cannot be described by a single projector.